Welcome to Alphanumeric Tricks. In last video, we have seen that solution of PDE by direct integration method. That is, in that video, we have seen that some of the basic problems using that is how to get the solution of some basic problems using direct integration method. Now we are going to see the standard types of first order nonlinear partial differential equations, which is of the form f of x comma y comma z comma p comma q is equal to 0. In this video, we are going to see the working rule to solve two types of equations, namely f of p comma q is equal to 0 and the Clairaut's form z is equal to px plus qy plus f of p comma q. Now let us see the video. And here we are going to see the methods to solve standard types of first order nonlinear partial differential equation. First order nonlinear PDE is of the form f of x comma y comma z comma p comma q is equal to 0. Here the partial derivatives p and q may occur other than in the first degree. In solutions to partial differential equations video, we have seen that some basic definitions of solutions, that is what are all the types of solutions available in partial differential equation and how to get the solution of those equations theoretically, that is working rule to get those solutions theoretically. We have seen that video. Now we are going to see what are all these standard types available in first order nonlinear PDE and how to get the solutions of those type of equations. Before going to start with these types, we will recollect some of the definitions which we have already seen. First one is complete integral or complete solution. This contains the number of arbitrary constants is 2. That is, it contains only two arbitrary constant, which is equal to the number of independent variables in our problem. Because the first order PDE we have two independent solutions, two independent variables x and y. So the solution must contain two arbitrary constant in complete solution. And the particular integral is obtained by giving particular values to the arbitrary constants in the complete integral or complete solution. Now we will see what are the standard types available in first order PDE. Type 1, f of p comma q is equal to 0. That is, equation contains only the p and q terms, not x, y and z. Next type is Clairaut's form, which is of the form z is equal to px plus qy plus f of p comma q. That is, the equation first term is always px and plus second term is always qy and third term is function of p and q alone. Next one is type 3. In type 3 we have three cases. First case is f of x comma p comma q is equal to 0. That is, in your first type the problem is having only p and q alone, whereas in case 1, that is type 3 case 1, along with the p and q, x only, the x term is present, that the variable x alone is present. So you have f of x comma p comma q is equal to 0. In case 2, along with the p and q, y is present, so f of y comma p comma q is equal to 0. In case 3, along with p and q, z is present, not x and y. So only z, p and q alone is present in your problem. Now in case 4 or type 4, separable equations. That is, f of x comma p is equal to phi of y comma q. That is, the equation contains the variables x, y, p and q. Z is not present in type 4. And you have to separate x terms together and y terms together. Here p is dou z by dou x, which is related to x. So we have to combine x and p. and q is dou z by dou y, the derivative which is related to y, so we combine y and q. These are all the standard types available in first order nonlinear PDE. But in physical nature of the problem, we can't predict that always the equation may occur in any of these four types. It may occur in different equations also, but how to solve those problems? We have another type, that is equations reducible to standard forms. That is using change of variables. Those type of equations can be converted into any of these four types and we can get the solution. In this video, we are going to see only first two types, that is type 1 and type 2. Alone we are going to see now, that is how to get the solution of type 1 and type 2 problems. And next video, type 3, type 4 and type 5 solutions will be given. Now we start with the first type problem, which is of the form f of p comma q is equal to 0. Now for the given problem as equation 1, we have to assume that the complete solution of this type of problem f of p comma q is equal to 0 is z is equal to ax plus by plus c. Number that equation as 2. Here we have to find out the complete integral for this type of problem, first type of problem. In your you know that complete integral consists of two arbitrary constants, but here in assumed solution we have three arbitrary constants are there, so you have to reduce this 3 arbitrary constant to 2 arbitrary constant. For that we have to assume that p is equal to a and q is equal to b. We have to assume that, or otherwise you remember this way, you have to differentiate this assumed solution with respect to x and y. We get p is equal to a and q is equal to b. This is substituted in the given problem 1, then you get f of a comma b is equal to 0. And using this relation, or that is using this relation and the given assumed solution, we have z is equal to ax plus by plus c, where arbitrary constants a and b are related with this function relation f of a comma b is equal to 0. Now we have to solve for the constant a or b. That is, if you want to find out the value of a, then you have to take b terms to right hand side, and if you want to find out the value of b, then you have to take other terms to right hand side, get the value of b. So you can write b is equal to phi of a, that is when you're taking b one to one side and a to other side, it's another equation you got it. That's why we are using the different function phi here, or a is equal to phi of b. Now in this video we are using b is equal to phi of a to get the complete integral. So substituting b is equal to phi of a in equation 2, then we get z is equal to ax plus b is replaced by phi of a into y plus c. Now your three arbitrary constants a, b and c is reduced to two arbitrary constants a and c, which is our required complete integral. And this we have two arbitrary constants a and c. Now we have to find out the singular integral. How will you get the singular integral? From complete integral we can find out the singular integral. That is, you have to eliminate the arbitrary constants available in complete integral, and using the rule that is the dou z by dou a is equal to 0 and dou z by dou c is equal to 0, we have to eliminate the arbitrary constants a and c. If you want to know about this rule, this is explained in solution of partial differential equations video. The link is available in the description box. Please refer to it. Now we will see how to eliminate the arbitrary constants a and c. Here you have to differentiate the given problem, that is a complete integral, with respect to the available arbitrary constants in the complete integral, not the independent variable. That you should remember. So you have to differentiate equation 3 partially with respect to the arbitrary constants a and c. Then we get, that is differentiation of az with respect to a is dou z by dou a, but using this rule, dou z by dou a is equal to 0, this term is equal to 0, is equal to differentiation of ax with respect to a becomes x, because x is constant when you're differentiating ax partially with respect to a, and the differentiation of a with respect to a is 1, plus y is constant when you're differentiating this with respect to a, and differentiation of phi of a with respect to a is phi dashed of a, plus differentiation of c with respect to a becomes 0. So you get the equation 0 is equal to x plus phi dashed of a into y, and we have to differentiate complete integral 3 with respect to the arbitrary constant c here. Now when you're differentiating this with respect to c, you have dou z by dou c, that value is taken to 0, is equal to differentiation of ax with respect to c becomes 0 because ax is constant, and plus differentiation of phi of a into y with respect to c is 0 because this is also constant, because we are differentiating with respect to c, remaining terms are taken as constant, plus differentiation of c with respect to c is 1. So 0 is equal to 1, we got it, which is an impossible result. So it is not at all possible. So we can't find out, or you can say that it is an absurd result. So we can't find out the singular solution using this term. That is, we can't eliminate the arbitrary constant a and c because the impossible result is obtained. So you conclude that no singular solution for this type of problem f of p comma q is equal to 0. And one thing you should remember, when you are replacing this b is equal to phi of a, we get to the, you have to eliminate the arbitrary constants a and c. Suppose you are using a is equal to phi of b here, then you get that is a b and c. You have to differentiate this with respect to b and c and get the singular solution. That thing you should remember. Now we will find out the general integral. How to get the general integral for type 1 problem. This is also, that is, in general integral you have to reduce the two arbitrary constant in complete integral to single arbitrary constant with the substitution is, that is, one constant is written as the function of the another one. So using that rule you have to convert the two constant in complete integral to single constant. That is, here you have a and c is present here, the constant a and c are there. So you have to write a is equal to f of c or c is equal to f of a in this complete integral. In our problem we are using c is equal to f of a, then your constant, two arbitrary constant in complete integral is reduced to single arbitrary constant a alone. That is, z is equal to ax plus phi of a into y plus c is replaced by f of a. And this is also explained in solution of partial differential equations video. Now you have to differentiate this equation 4 with respect to the arbitrary constant a. Here we have only one arbitrary constant is there, so you have to differentiate this with respect to that arbitrary constant a. Then you have dou z by dou a, which is equal to 0, is equal to differentiation of ax with respect to a becomes x, because x is constant, differentiation of a with respect to a is 1, plus y is constant into differentiation of phi of a with respect to a is phi dashed of a, plus differentiation of f of a with respect to a is f dashed of a. Now using this 4 and 5, we try to eliminate the arbitrary constant a, then we will get the general integral for the given type 1 problem f of p comma q is equal to 0. Now we will see the next type. Type 2, Clairaut's form z is equal to px plus qy plus f of p comma q. Number that given Clairaut's form to be 1. Equation number 1. Here also we had to find out singular integral, complete integral, singular integral and general integral. Now we will see the complete integral for this type 2 problem. In Clairaut's form, the finding complete integral is very easy, because here you have a two arbitrary two independent variables x and y, and here the equation is contained p and q alone. So if you substitute the p is equal to a and q is equal to b, then you get the two independent variables and two arbitrary constants is present in your equation. So directly we get the complete integral. So substituting p is equal to a, q is equal to b in 1, we get z is equal to a, p is replaced by a, so ax plus q is replaced by b, so by plus f of a comma b. So this is the required complete integral for Clairaut's form. Now we have to find out and here a and b are arbitrary constants. Now we have to find out the singular integral for this type 2 problem. As usual, singular integral is, you have to find the singular integral, you have to differentiate the given complete integral with respect to the available arbitrary constants. Here why we are using available arbitrary constant is, in previous type 1 problem, according to our substitution we get arbitrary constants are a and c, but here in type 2 problem we get a and b is the arbitrary constant. So depending upon our substitution, the constants may vary. So that's why we have to differentiate the given problem or complete integral with respect to the available arbitrary constants. And using the rule dou z by dou a is equal to 0, and here also the same condition, dou z by dou b is equal to 0. That is, you have to use the rule depending upon the number of arbitrary constants. Here a and b are arbitrary constants, so we are using the rule dou z by dou a is equal to 0 and dou z by dou b is equal to 0. Now you have to differentiate equation 2 partially with respect to a and b. When you are differentiating equation 2 with respect to a, then dou z by dou a, that is equal to 0, is equal to differentiation of ax with respect to a becomes x, plus differentiation of by with respect to a is 0, because by is constant, plus differentiation of f with respect to a is dou f by dou a. So we get x plus dou f by dou a is equal to 0. Number that is 3. Now you have to differentiate 2 partially with respect to b. So you have dou z by dou b, that is taken as 0, is equal to differentiation of ax with respect to b is 0, because ax is constant, plus differentiation of by with respect to b is y alone, because y is constant when you are differentiating with respect to b. So y right as it is, differentiation of b with respect to b is 1, plus differentiation of f with respect to b is dou f by dou b. So we get y plus dou f by dou b is equal to 0. Number that equation as 4. Now using 2, 3 and 4, we had to eliminate the arbitrary constants a and b, then we can get the singular integral of the Clairaut's form, z is equal to px plus qy plus f of p comma q. And here in this second type of problem, always have a singular integral, but first type of problem, singular integral is not at all possible, because we get the absurd result. So singular integral is not obtained for first type of problems, and rare case it may occur. And similarly in type 2 also we can singular integrals always exist for this type of Clairaut's form. Now we have to find out the general integral for type 2 problem. Here also you have to use the substitution b is equal to phi of a, that is you have to use one constant as a function of another one, that is we take in complete integral we have two arbitrary constants a and b, so using this we have to write a b is equal to phi of a. Using the substitution b is equal to phi of a, or you take a is equal to phi of b, that is one constant as a function of another one. This is also explained in solution of partial differential equations video. Now we have to substitute this in the complete integral, and this is, you should remember, this is also obtained from, that is general integral is also obtained from the complete integral. So substituting this in 2, we get z is equal to ax plus b is replaced by phi of a into y plus f of a comma b is replaced by phi of a. Number that equation as 5. Now the equation is reduced to arbitrary constants and complete integral is reduced to single arbitrary constant. You have to differentiate this with respect to that single arbitrary constant a. So partially differentiating this with respect to a, then we get dou z by dou a, which is equal to 0 is equal to differentiation of ax with respect to a becomes x plus phi of a into y with respect to a is y is constant, right, as it is. Differentiation of phi of a with respect to a is phi dashed of a plus differentiation of f with respect to a is dou f by dou a. That is here you have to just write dou f by dou a. If we doesn't have the function phi of a, so we just write dou f by dou a. Number that equation as 6. Now using 5 and 6, we have to eliminate the arbitrary constant a, then we can get the general integral of equation 1. That's all for today's video. If you have any doubts in this, please provide in the comment section. Thanks for your time and thanks for watching. We will see in the next video with another 3 type of problems and with solutions. Thank you.